We return to the difficulty we had of getting the spark. As we shall see immediately, this will be resolved by a new definition of the mutual coherence. Just to put things into their proper perspective, spark could be useful for evaluating the optimality of a sparse solution. However, computing it is daunting, so we cannot really know what is the spark of a general matrix A. As said above, we will try now to generalize the mutual coherence beyond just serving the 2-ortho case. This will help in evaluating the spark. Let's start by recalling how the mutual coherence was defined for the 2-ortho case. We took the inner products of all the pairs from psi and phi and searched for the maximal absolute value. We also saw that this is just as computing psi transpose times phi and then seeking the maximal absolute entry in this matrix. The coherence seeks the two most alike atoms in A, where this is measured by their inner product. The higher it is, the closer they are. Another, much more constructive way to look at the coherence is this. Compute the Gram matrix A transpose A. Doing this for the 2-ortho case, we get this 4 blocks structure that has n by n identity matrices on the main diagonal blocks, and psi transpose times phi and its transpose on the other blocks. So we can suggest an alternative definition for the coherence. Mu is the maximal off-diagonal entry in absolute value in A transpose A. Observe that in this new definition, the many zeros that we encounter in psi transpose psi and phi transpose phi do not influence the definition. The beauty in this new definition is the fact that it is not related at all to the inner structure of A, being the 2-ortho. So how about using this definition for the general case? Based on this idea, we now present a new definition for the mutual coherence. On one hand, this definition generalizes the one we used for the 2-ortho case, and on the other hand, it is able to treat any matrix A. Given a matrix A, the coherence is defined as the maximal absolute inner product between its columns, but as can be seen here, we normalize the inner product by the two columns norms. Put differently, if we take all the columns of A and L2 normalize them, then the mutual coherence mu is given as the maximal absolute inner product. Let's assume that the columns of A are indeed normalized. In this case, we compute the Gram matrix A transpose A and get the square m by m matrix G. This matrix is symmetric. Its main diagonal contains 1s, and mu is simply the maximal absolute value in the off-diagonal entries. This brings us to an obvious alternative definition of the mutual coherence. Given A with normalized columns, mu is the maximal absolute value in the lower triangular part of the Gram matrix G. And now we get to the punchline result. The mutual coherence we have just defined is tightly related to the spark, as this theorem states. The spark is bounded from below by 1 plus 1 over mu. So getting a lower bound for the spark is rather easy, since computing mu is simple and cheap. Armed with this, we have the following important consequence. If we replace spark by its mutual coherence lower bound in both the uncertainty law and the uniqueness requirement, we get the following theorem that poses the two in much simpler terms. While these new statements are weaker, posing more restrictive conditions, they are using computable bounds. In the next part, we shall prove the coherent spark relationship that enabled this leap.